Okay, I'm Yoshihiko Suzuki from Kyoto University, Japan. First of all, I'd like to briefly appreciate Professor Igor Medic and Antonio Namara for inviting me this great opportunity to talk here. I came to Toronto for the first time. I really enjoyed Toronto in, of course, scientific and non-scientific ways. Thank you. So my title of the presentation is here. That is slightly changed from that I sent to you in the office. The Koopman analysis of a singular system, because Igor said to me about please try to show the new results on the Koopman operator. That's why I tried to introduce the recent of my works on the singular system and their analysis by the Koopman operator theory. So here, this is the motivations. The motivation here is to try to develop a comprehensive theory of Koopman operators for, the singular systems. System described by the nonlinear differential algebraic equations or singularly perturbed ODEs. In particular, I emphasize on the 2 points. First one is not only smooth dynamics of a system, but also the non-smooth dynamics, including the jump behaviors, or also they include the case of the nonlinear hybrid systems. The second one is we focus on the global structures. Of course, we know it's a very traditional way of the local asymptotic expansion for the singularly perturbed systems. But in this case, I try to do more emphasis on the global structures. Okay, the broad applications appears in the systems. For example, the computation, the climate science, including some model of the deductions, and biology, chemistry, and engineering, systems control, and so on. Here is the motivation. Okay, so this is outline of my presentation. I have the 3 topics in my talk. First of all, I'd like to analyze index 1, or semi-explicit DAEs with smooth dynamics. This is one kind of the theory, Koopman operator theory for dynamic systems on analytic manifolds. Second, we move to a more singularly perturbed case where we analyze the singularly perturbed fundable oscillators. Fundable oscillator appears often in this session. And here I try to identify the spectral signatures of singular perturbations, also spectral identifications of non-smooth dynamics. And finally, we mentioned about the so-called analysis of Koopman resolvent to capture such dynamics in the frequency domain, in the Laplace domain. Okay, so let's move to the part 1. So the analyze index 1 DAEs with smooth dynamics. This is my solo work published in IFAC Papers Online 2021. And here, our target is here, index 1 or semi-explicit DAEs. Now, x is some variable, y is also variable. X is so-called differential variable, y is algebraic variables. And capital F and capital G, they are nonlinear vector fields that are assumed to be smooth. Now, this type of system appears in broad applications. For my experience, I'm working on more the power systems. The power system engineers always using this type of model to capture dynamics of the power systems. In this, the differential equation describes the dynamics of generators, equipment, and so on. And algebraic equation describes the so-called conservation law of power. Okay, the current question is about here, how do we characterize not only smooth dynamics, but also non-smooth dynamics of the singularly perturbed, these DAEs, in the Koopman operator frameworks. So part 1, I try to answer the smooth case. And the non-smooth case is relatively complicated, so I'll work on in the part 2. To answer the questions for the non-smooth case, we restrict our analysis in the so-called regular set. The regular set is defined as follows based on the algebraic equations. And here's the Jacobian matrix of G is respect to the Y. Y is algebraic equation, the inverse exists. In this set, there exists a transformation phi from X to Y. So based on this transformation, we can transfer this DAE into the regular ODE. In this situation, we can apply the general theory of regular ODE system to the DAE. Okay, so I try to introduce the Koopman operators. Now we have the considered stable equilibrium point of the DAE system on the regular set with a non-empty basis of attraction, capital A. on the domain of the attraction, we can do so-called semi-flow, that is forward invariant. And also by using these flows and also the observable f on the regular set, in this case on the domain of attractions, that we assume that this function is continuous. And then for the Koopman operator ut defined as follows using the semi-flow on the domain of attraction on the regular set. This is a natural extension of the OD result to the DA systems. And as a nice byproduct of this formulation, we can say the time evolution of the algebraic variable y. This y is represented by so-called transformation from x to y. So the y is now observable. So the time evolution y is driven by the Koopman operator u. That is good for the following the spectral expansions. Okay, now I introduce Koopman operator. So then spectral expansions. Now you assume, like Alex, we presume f and g are analytic. Also, the observable is also analytics. And also, we denote the n linearized eigenvalues, they are distinct. And then for the DAE system with smooth dynamics, the time evolution of x, the differential variable, is decomposed into the point spectrum of the Koopman operator. That is a parallel series of the ODE case. And also, this implies that this Koopman operator now has the point spectrum only. In addition to this, as a corollary, the y is algebraic variable y is also holds for the same spectral expansions in terms of the common Koopman point spectrums. That is good for some application. For example, in my case of the power grids, y is just measurable. X is not measurable. So the y is, we can know the time series of y. So from getting the data of y and its spectral expansion, we can know the Koopman operator. That is good for the application in my case. Okay, this is the last of the part one. With a simple example, it's the 2D systems. X is 1D and y is 1D. So the 2D space and somehow the constraint set is 1D curved, denoted by the L. All trajectories of the DAE live in on this line. And here, this is for the two cases, you can see the multiple stable equivalent points, here and here and here. Our theories show that, so that for each domain of the attraction of a stable equivalent point, the x direction dynamics of x and y are decomposed in terms of the point spectrum of the Koopman operator. For the case of this, that we can derive analytically the eigenvalue and eigenfunctions like this. This is the application of our theories. And also in the lower case, this implies one limitation. You can see on the upper branch of F, you can see the trajectories converted to S, and finally, somehow, a loss of the uniqueness of the solutions. This case is exclusive in the theory in the part one. This is one kind of the non-smooth dynamics appearing in the DAE that I analyzed in part two. Okay, so let me move to the part two. It's the analysis of singularly perturbed van der Pol. It's not regular, singularly perturbed van der Pol oscillators. So now I try to derive the spectral signatures of singular perturbations and also analyze the non-smooth dynamics. This is just appeared in the archive last week. This is joint work with my student in Kyoto, it's Mr. Katayama. So I focus on the so-called very famous singularly perturbed system. The singularly perturbed van der Pol oscillator is like here. Now you can see the small positive parameter epsilons. Okay. And then this is also famous phase portrait of x and y. In this case, epsilon is here. So x is so-called fast variables, while the y is the slow variable. So the x direction is fast and the y direction is slow. In this portrait, W is the null line of F. And also the W plus W minus is so-called attracting part of the null line of W, so W plus W minus. I mean, now we can take initial condition x0, so the trajectory is quickly converge approach to the W plus, and then slowly moves along the W plus. This is some kind of typical of the relaxation oscillations due to the presence of the epsilon, the small epsilon parameters. And also after this, so the trajectory reaches J plus the point, and then again quickly move to the W minus, and also slowly move to along W minus, and again the quick jump. So we see the relaxation oscillation that is a stable limit circle. This is of course due to the presence of small epsilons. My question is about to locate any Koopman spectral signature of singular perturbation. Okay, to answer this question, first of all, I introduce the 5 flows. Okay, this is again the phase portrait. This is the original system. So in this system, we say that this is a singularly perturbed ODE in a slow time scale. By using the time transformation t is equal to tau over epsilons, we can derive equivalent another singularly perturbed ODE. This is in a fast time scale. Now we have the 2 flows. And now by taking the epsilon is equal to 0, that is the singular limit, we can derive the slow subsystem and the fast subsystem. This slow subsystem is the index 1 DAE that we analyzed in the part 1. And the fast subsystem is typically set the boundary layer ODE. And now we have 4 systems. Associated for the dynamic system, we can derive the 4 flows. The 2 flows are related to the singularly perturbed system, including the small epsilon. And also, in addition to this, as a singular limit. In the singular limit, we can think about so-called hybrid flows. That is a combination of the discontinuous jump and continuous flows. We say that this type of flow is denoted by here. This is a hybrid flows. So now we have totally the 5 flows. So the next, we try to introduce the 5 Koopman operator for the 5 flows. So this is somehow the comparison between the flows and the Koopman operator. For the 2 flows for the singularly perturbed system, we introduce the 2 Koopman operators. And also for DAE, the slow subsystem, we introduce the Koopman operators. And for the same case for the fast subsystem. In addition to this, for the hybrid flow, we introduce the Koopman operator, U tilde 0 slow. So my question is about how about the spectral signatures for the 5 flows? That tells us about the spectral signature of the singular perturbations. Now we focus on the 2 Koopman operators for the singularly perturbed systems. We visualize the Koopman eigenfunctions in the x and y plane. Okay, this is somehow the principal eigenvalues, eigenfunctions. As Igor introduced in his talks, this system has the 2 principal eigenvalues that is related to the angular frequency of the limit circle and the new epsilon that is decay rate, characterized by the Floquet exponent. And then now epsilon is 1, epsilon 0.1, and 0.01. So that is the singular perturbations, the parameters. And then you can see that the eigenvalues associated with the angular frequency of the limit cycle is somehow converted to the finite values. On the other hand, this is the second eigenvalue that's related to the Floquet exponent, is diverge. This is one kind of the spectral signatures of the singular perturbation. In addition to this, I show the level set of the Koopman eigenfunction for the first and the second eigenvalues. Here, this is also Igor introduced in his talk, is about so-called level sets of the isoclones. The other one is also related to, so it's exactly the same as the isostables that Alex and Igor developed in their papers. And here I can point out the 2 distinctive features of the visualizations of eigenfunctions. First one, you can see that in this, so the epsilon is 1, 0.1, 0.01, is the shape of the level set like the parallel to the x-axis. That is clearly due to the time separation of x and y, because x is fast and y is slow. So due to this time scale separation, this type of the shape happens. And the second one is about the close to the origin. You can see here some kind of drastic change of colors. implying that large change of the functions. Now, this is kind of also the specific signature of singular perturbations. I'll try to analyze this point in detail in the next page. So I focus on the shape of the Koopman eigenfunctions and also the singular limit at epsilon is equal to 0. As I talked about in the last slide, so the first eigenvalue is converted to finite values, and the second eigenvalue is diverge as epsilon is equal to 0. And also associated with this, so that you can see the shape of the Koopman eigenfunctions from the direction of the x. Now, so the around the 0, that is also, we can say, it's close to the repelling part of the constraint manifold. And close to this portion, you can see the shape is very sharp. In addition, also, as a singular limit, this associated function has a clear discontinuous point around the origins. So I think that this kind of the singularity or discontinuity of the function provides the specific signatures of the singular perturbation in the case of this. Okay, so finally, I focus on the hybrid case with the singular limit of the Koopman operator itself. Now we focus on the hybrid flow, that is the discontinuous jump and continuous flow, that's the combinations providing the hybrid flow. And then we have the theorems. One, the Koopman operator has a point spectrum only. And also their Koopman eigenfunctions are discontinuous along the two lines, B minus and B plus. These lines are important object to distinguish the different type of the trajectory. For example, is above B minus 1. Here is the initial condition and then converted to the W plus. And on the other hand, and below the B minus 1, converted to the W minus. The two types of different trajectory are distinguished by the B plus and B minus. That's why also implication we have the discontinuity of the Koopman eigenfunctions provides a global information for the hybrid flow. Okay, so I move to the last part 3, so analysis of Koopman resolvent. So this is some kind of different idea, but I try to analyze such singular dynamics in terms of the Laplace domains. Also, this is a joint work. I forgot this. With the Alex and Eagles, published in 2021. Okay, now this is the key tables. Here is somehow the question is about how to identify the mathematical meanings of the Laplace domain analysis of nonlinear systems. As you know so much, linear systems, widely we use Laplace domain theory to characterize the property of the systems. But our paper shows that the Koopman resolvent, that is the resolvent operators of the Koopman generator L, that provides the Laplace transforms of the output signal of generated by the nonlinear autonomous dynamical systems. Now, this is a clear answer in a mathematical way. So in these formulations, f is observable. That's why this is just put the measurable function, function of the measure. So all the system dynamics is reflected by this Koopman resolvent. That's why we need to analyze the resolvent directly. To this, I introduce the spectral expansion of the Koopman resolvent. We have the many theories, but this is one of the theorems related to the system with stable limit cycles. In this case, we can decompose Koopman resolvent in terms of like this. Here is the poles of order 1 correspond to the Koopman eigenvalue. And so this type of the expansion is good to analyze the nonlinear dynamics in terms of the Koopman resolvent. Finally, I try to connect this idea to, again, the singular perturbed van der Pol oscillators. This is, again, the singularly perturbed van der Pol oscillator with small epsilons. Our theory implies that the Laplace transforms, the two states, x and y, are represented as follows. This is theorem. And here, the pole of order 1 describes the eigenvalues of the associated Koopman operator to these systems. And also here, now we have the epsilon, so the eigenvalue also is denoted by the epsilon. Also, the decomposition implies that stationary poles persistent under the singular perturbations also non-stationary poles is not persistent under the singular perturbations. So this is also that provides the complex functions. So my idea is about the discontinuity of the functions. It can be analyzed in terms of the property of the complex functions. That is interesting topics, but this is still in our future work. Okay, so I summarize my presentations. I talked about the three topics, and the DAE and the singularly perturbed system and the resolvent. And finally, I tried to emphasize on the 2 points. First one, I introduced the operator formalism for the not only smooth but also non-smooth dynamics. The second one also we provided the spectral signature of the singular perturbation. That's the singularity of the functions. So I guess the singularity of function plays a important clue to analyzing the global dynamics, global structure of the phase space for the singular systems. We have the many follow-up studies, including the more than 2D problems, so the Koopman embedding of singular systems, and finally the application to climate science and chemistry. So that's all I have. So again, I thank you to my student, Katayama-san, and Alex and Igor and Professor Antonio Navarez. Thank you very much.